Since December 1972, no human being has traveled beyond low Earth orbit. Artemis II is the mission designed to bridge that 50-year gap, serving as a live-fire test for the hardware that will eventually carry out a lunar landing. The vehicle tasked with returning humans to deep space is the Space Launch System, or SLS, standing over 320 feet tall and producing 8.8 million pounds of thrust. It is the most powerful rocket that NASA has ever successfully launched. Sitting at the very top of that massive rocket is the Orion crew module, which this crew specifically named Integrity. While Orion has flown empty, its complex deep space life support systems, responsible for everything from air filtration to thermal regulation, have never been proven with a human crew. Trusting those unproven systems was a historic 4-person crew. Commanded by Reed Wiseman, the team included mission specialists Christina Koch and Canadian Jeremy Hansen, along with pilot Victor Glover, seen here standing in front of the Orion structure during its final assembly. The mission functioned as a high-stakes verification of the physical infrastructure required for human survival in the absolute hostility of deep space. That hostility becomes most apparent when coming home. After the uncrewed Artemis I test flight, engineers inspecting the capsule found areas where the AV coat heat shield had chipped and cracked away, which is a destructive process known as spalling. This cross-section diagram shows how the failure occurred. Hot gases became trapped inside the material during re-entry, creating localized pressure buildups that fractured the surface layer and caused chunks of the shield to break off prematurely. To bypass the risk of a full redesign, NASA modified the mission's math. By changing the spacecraft's trajectory for a steeper, more direct descent, they could significantly reduce the duration of the thermal peak during re-entry. All 4 astronauts strapped into Integrity, knowing full well that their survival depended on these adjusted thermal calculations being exactly right. On April 1, 2026, the SLS punched through the atmosphere, but instead of heading straight for the moon, the upper stage placed Orion into a highly elliptical high Earth orbit for its first 24 hours in space. This initial orbit served as a safety checkpoint. It allowed the crew to stress test the life support systems through physical exercise and practice manually piloting the capsule while they were still close enough to Earth to abort if the system failed. Once Mission Control verified the hardware was holding stable, Orion fired the main engine on its European service module. This trans-lunar injection maneuver provided the necessary thrust to leave Earth's orbit and begin the trek toward the moon. Looking at this orbital map, the spacecraft was now locked into a hybrid free return trajectory. This specific route uses the moon's gravity to grab the capsule, loop it around the far side, and naturally throw it back toward Earth. While standard lunar orbits require engine burns to get home, this gravitational slingshot acts as a failsafe. If Orion suffered a total engine failure, the physical path itself guarantees the capsule will head back to Earth. By engineering the physical route to include this failsafe, NASA ensured the crew would return to Earth regardless of propulsion status. By flight day 6, Orion entered the moon's sphere of influence. As the capsule passed behind the lunar far side, the mass of the moon blocked all radio signals, cutting communications with Earth for 40 minutes. During that pass, the crew traveled 252,756 miles from Earth. That distance broke the all-time record for humans in deep space, previously set by Apollo 13. Emerging from the blackout, the astronauts captured this view. You can see the desolate lunar craters dominating the foreground as the Earth sets against the absolute blackness of space. While the crew observed the surface, an onboard payload named Avatar was working to measure radiation. It exposed human tissue analogs to the deep space environment to gather the first data on how high-energy particles affect biology outside of Earth's magnetic field. The lunar flyby yielded vital biological data, proving the spacecraft's interior remained shielded enough for human cells to survive the radiation levels found at these record-breaking distances. On flight day 10, the capsule rapidly approached Earth. The crew jettisoned the European service module, leaving only the Integrity crew module to face the final phase of the mission. At an altitude of 400,000 feet, Integrity hit the upper atmosphere, traveling at Mach 35. That is an astonishing 24,852 miles per hour. That extreme velocity compresses the air in front of the capsule, generating a glowing sheath of superheated plasma. The AV-coat heat shield had to endure temperatures between 3,000 and 5,000 degrees Fahrenheit. Inside, the steeper entry angle meant the crew endured severe physical forces, absorbing up to 3.9 Gs as the atmosphere aggressively slammed the brakes on their speed. But those adjusted trajectory calculations held up under the pressure. The ablative material eroded exactly as the models predicted, protecting the underlying titanium structure of the capsule. Surviving this 6-minute plasma inferno was the ultimate dynamite test of the mission. It was the moment the engineering was proven to be structurally sound. At 23,400 feet, drogue parachutes deployed to stabilize the spacecraft. Then, at 5,400 feet, the 3 massive main chutes opened, slowing the 20,000-pound capsule to a gentle 20 miles per hour for splashdown. Integrity landed safely in the Pacific Ocean, where the crew was quickly recovered by Navy and NASA teams aboard the USS John P. Murtha. The successful completion of Artemis II provided the definitive validation of the SLS and Orion hardware. With these systems now proven with a human crew, the path is open for Artemis III and a permanent return to the lunar surface.